So what I'd like everybody to do is please write this down. The summation from n equals 1 to 4 of 4n plus 1. Please write this down. Summation of n equals 1 to 4 of 4 plus 1. For those of you who were here yesterday, please expand this. Please expand this. Expand. If you can't expand it, don't worry. I'll show you in a second. It's no big deal. Okay, Avery, can you tell us what you expanded this to be? Very good. So, boys, where did she get the 5? She plugged in 1. 4 times 1 is 4 plus 1 is 5. Where did she get the 9? She plugged in 2. 4 times 2 is 8 plus 1 is 9. Where did she get the 13? She plugged in 3. 4 times 3 is 12 plus 1 is 13. And she got 17 because she plugged in. Why did she stop at 4? Because 4 is this number up here. This is where we start. This is where we stop. Yes. All right, here we go. So remember, we talked about none other than Mr. Frederick Gauss yesterday. And we said, Frederick, how do you add up the numbers 1 plus 2 plus 3 plus ... plus 98 plus 99 plus 100? And those numbers all add up to what? 5,050. How did Frederick at age 8, how did he add all those up so quickly? He took 1 plus 100 and got 101. He took 2 plus 99 and got 101. He took 3 and plus 98 and got? So he said they all add to 101. And how many sets are there? There's 50 because we had 100 numbers and we put them into pairs, right? So 100 divided by 2 is 50 times 101 was 5,050, and that's how he did it. Let's see if his method works here. Okay, you would take the first one plus the last one. What's the first plus the last? 22, and how many sets are we going to have? 4 divided by 2. So you take the number of terms, which is 4, and divide it in half. 5 plus 17 is? And 22 times 2 is? 44. Does this add to 44? Yeah, 5 plus 9 is 14. That's 30. Adds to 44, doesn't it? So if you simply take the first term plus the last term and multiply it by the number of terms divided by 2, we said the following. We said the first term plus the last term multiplied by the number of terms divided by 2, you will get the sum. So what I'd like you to do right now is I would like you to figure out what do the numbers 1 plus 2 plus 3 plus ... plus 438 add up to. See if you can figure out what all those numbers add up to. First term plus the last term multiplied by the number of terms divided by 2. Try to come up with it. Go. That's the number of terms. There's 438 of them. Okay, so I should have 1 plus 438 times 438 divided by 2. What did you get? 96,104. Is that what we have? Look at how quickly you came up with that sum. Wouldn't you agree that Frederick was pretty sharp to come up with that on his own? Yeah, and one of the greatest minds that we've seen, this makes summation much quicker. But the question is does it work for all numbers? We talked about that yesterday. Marissa, and probably crying a little bit. So, all right? So here we go. Write that down. We're going to sum from k equals 1 to n of k. We're going to expand this. We're going to see what it results to, and we're going to do a proof of it. If I want to expand this sum, what do I first plug in for k? 1, and you get 1. For those who weren't here yesterday, can you guys tell them what does this sigma thing mean? It means it means sum, so we put down addition. And then we go to our next term. What do we plug in next? And when you plug 2 in for k, you get 2. And then we plug in 3, and we get 3. And then you plug in, and you get 4. Getting a little tired of that? Okay. So we're going to do dot, 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 dot. What is the last thing that we plug in? N. And we plug in n for k, you get n. So Gauss's suggestion was that if you add those up, you get n times n plus 1 divided by 2. Do not think geometry because it is not. We are going to prove this to be true. And we will prove by induction. It is one of the most brilliant ideas that we've come up with. It's absolutely beautiful. There's 3 steps to mathematical induction. And the first one is as follows. Show the rule is true for the first few cases. Have we gotten this to work out? We have. We need to show whoever is reading the proof that it works for at least a couple cases. So I'm going to show for case n equals 1. I'm just going to say, does it work for just that very first situation? Suppose I want to add up all the numbers between 1 and 1. What do those add up to? 1. So let's try. We're going to say 1, is that equal to? Now, how many numbers did we add up? 1. So we'll plug in 1 for n. 1 times 1 plus 1 divided by 2. Are those two expressions the same? So this formula works when we've just added up the very first number. We get 1, we are good to go. Now, I'm not really convinced that it continues to work. I need to see another case. We're going to do case n is equal to 2. How many numbers do you add up now? We add up 2 numbers. What are the 2 numbers you add up? So I do 1 plus 2. We're going to see if that is equal to, what do we now plug in for n? 2. Case n equals 2. So we get 2 times 2 plus 1 divided by 2. Well, I know that 1 plus 2 is 3. Does this side come out to be 3 as well? It sure does. That was kind of snazzy. I like that. I wonder if it works for case n equals 3. Anybody want to guess whether or not it works for case n equals 3? Let's see. How many numbers do I add up now? 3. I do 1 plus 2 plus 3. And what do I now plug in for n? I plug in 3, and I get 3 times 3 plus 1 divided by 2. Let's see, I have to do a little thinking here. What's 1 plus 2 plus 3? 6. And does this give me 6? 4 times 3 is 12 divided by 2 is 6. Hey, I got it. Are you feeling convinced that this formula really works? Are you convinced, Laura? Are you convinced, Ella? Are you convinced, William? William's not, so let's try another. You'd like to jump to 7. Okay, let's try 7. You should really do them in order, but to make you happy, let's do 7. No, wait. So you technically only have to do 1. But usually I encourage people to do at least 2 or 3 to feel like you get a feel for what the formula is doing. Let's just try 7 to appease Ella, okay? So we have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. 7 times 7 plus 1 divided by 2. Now, I got to kind of look at both of these. 1 plus 2 plus 3 plus 4, I'm good at that. That's 10. 10 plus 5 is 15. And 15 and 13, that makes 28. So let's try that. So 7 plus 1 is 8, divided by 2 is 4, times 7 is 28. Okay, have we shown it works for a few cases? That's kind of satisfying to see that formula work out, right? Like you're like, hey, I'd like to get myself some of those formulas, right? And we can actually make up those formulas. I'll show you how someday. It's pretty cool. But let's move on to the second step of the proof, because William, are you convinced now that it works? Good. So second step is assume the rule holds true for case n equals k. Yeah. And this is called your inductive hypothesis. And it's important because you end up using this every single time. Now, I have to write out what the inductive hypothesis is. It says for case n equals k. So we're going to start with 1 plus 2 plus 3 plus 4. But what do I stop with? What's the last thing I plug in? K. I plug in k. And when you plug in k, what do you get? Just k, right? All right, now let's go to the other side of the formula. How many terms did we add up? K. So we plug in a k for n, and we get k times k plus 1 over 2. Does that look familiar? It's basically the same thing we started with. It's just instead of an n, we have a k, right? You might be like, well, that's just too easy, Mr. Gentz. That's super important and powerful, and we're going to use it. And that's all there is to the second step. First 2 steps are pretty easy, aren't they? I'm getting. First steps are pretty easy, right? Like inductive hypothesis or organic chem. I'm saying inductive hypothesis right now. Mathematical induction, that's where it's at. Okay, all right. Third one. So the nice thing is that the third one is a little bit harder, but it's really, there's not that much to it. Right now we're going to write it down, and then you're going to see the logic. Show the rule holds true for case n equals k plus 1. Please don't go if the bell rings. Okay, we're going to be right through it, but once you write this down, please put down your pencil. This is the whole point of the lesson. This is forget about math being algebra or anything like that. Algebra just becomes boring after a while. This is the beauty. Are you ready? N equals k plus 1. Okay, so watch this. We have works for. Okay, and then we have k, and we have k plus 1. Okay, so what have we shown that this works for? 1, 2, 3, and then we did 7. But we didn't show 4, 5, or 6. So let's just stop at 3. Okay, let's just stop at 3. So watch this. This is super cool. Okay, so k could be 3. Okay, k could be any of those. If we show it works for k plus 1, what is k plus 1? So we showed it works for 4, didn't we? So that means we get to add 4 here. So now it works for 4. Well, if we showed it works for k plus 1, then it works for 5. Okay, it works for 5, so we get to put it here with what it works for. So if it works for 5, then it works for 6. And if it works for 6, then it's going to work for... And then if it works for 7, then it's going to work for... And all of a sudden, we go to infinity like that, don't we? Do you see that? Isn't that beautiful? It's like this. This is the idea, and mathematicians give it this idea. They said, have you ever played dominoes where you like set them up and you tip them over? This is what they say. They say, you know, you take those first couple, 1, 2, and 3, and you give them a little push. Those are like K, and then K plus 1 just knocks all the rest down. That's the idea. And the logic behind it is absolutely genius. It's changed mathematics forever. So let's show that it actually works. Here you go. Yeah. Kind of an impressive individual, huh? Didn't do this at age 8, so. Okay. 1 plus 2 plus 3 plus 4 plus, how many do we add up? K plus 1. Now, instead of putting K plus 1 at the end, I'm going to put plus K and then plus K plus 1. And you're going to see why. So I have all of those. So now I'm doing K plus 1 terms. Now, what do I plug in for N now? K plus 1. And when you do that, you get K plus 1 times K plus 1 plus 1 divided by 2. I know you guys want to combine the terms there and make 2, but you can't. Sydney, you should really wake up. All right. So we've got that, okay? So what we have to do is we have to make the left side look like the right side. That looks like a problem, doesn't it? What did I tell you we were going to use? Does that look familiar, folks? Have you seen that written down on your paper somewhere? Isn't that what we wrote right here? What is this thing equal to? This is equal to? This thing is this right here, is it not? So instead of writing this, I can write K times K plus 1 divided by 2. What else is on the left-hand side? Yeah, plus K plus 1. I have to now make this thing on the left look like that thing on the right. I'm closer now, aren't I? How would you make this look like that? What could you do? Now here's where your beautiful algebra kicks in. Multiply by. Okay, so you want to create common denominators? Good idea. Let's do that. K times K plus 1 divided by 2 is equal to 2K plus 2 divided by 2. I just created common denominators like you said, right? We all good? Is this fraction is now all over 2. So let's figure out what we have on top. K times K is K squared. K times 1 and 2K will give us, whoops, sorry, I have that equal sign. No, it's supposed to be a plus. So 3K plus 2, right? So does that look similar to that? It's getting there. That's written in factored form, isn't it? Does this factor? What does it factor to? Yeah, K plus 1 times K plus 2, right? Does that look similar to what we have over there? Yeah, it's like I got the K plus 1. Now I have this K plus 1 plus 1. Isn't that the same as K plus 2? I could just separate the 2 into 1 plus 1, and they'll look the same, won't they? So let's do that last step. I have K plus 1 times K plus 1 plus 1, all over 2. And that's equal to exactly what we had on the other side. And our proof is done. We went from working for 3 cases to all of a sudden working to an infinite number of cases in a matter of minutes. Latin for that which was to be demonstrated has now been shown. It's a way to end a proof. And now I drop the mic. You guys have a great day. Go support those seniors at graduation. Show up on Monday ready to learn, Tuesday ready to learn, and I promise you, you will be good to go.